This is a project that we have been doing it together with ESA Lab, and that is almost done for part of it, and that this will be what I will present here. So let me see if that things works. NR, this is where we work. We are a research institute situated in Oslo. We perform contract research in AI and data analysis, and we have been around since the 50s. Of course, at that time, the AI was a totally different scale than we have today. But we have one big invention, and that is super big. That is object-oriented programming back in the 60s. That is Simula 67 programming language. Earth observation or remote sensing. It's a topic we will focus on here. So the benefits of using, let's say, satellite Earth observation is that it allows large-scale mapping and monitoring in inaccessible areas, like sea ice, far out to the sea, in the mountain areas and stuff like that. And it provides consistent, regular, and in some cases real-time data, and you can also sense in a lot of different modalities, so you can reveal different physical characteristics of the Earth. It is non-invasive and can be cost-effective. It depends on, of course, the methodology you choose to use. Satellite is, at least the satellite I will be talking about here, they are freely accessible, but there are others that you need to pay for data as well. So this delivers objective data for research and decision making. And if you think of how it works, a satellite just, like at least these Earth observation satellites, they orbit often in the polar orbit, which means that they're crossing the north and south poles of the Earth. And it just goes around in a circle, and the Earth rotates, and it covers the ground at different locations due to that. So you can see here that for this example, that the footprint of an image that you acquire using a satellite needs to be at some size in order to have, let's say, a daily mapping of the Earth. So many of these satellites are not able to do that. The two different modalities I will be discussing or using here in this model is radar imaging and optical imaging. Optical is based on that the sun illuminates the scene, and you just measure the optical data that you receive that hits the camera. That is, but in radar it's different. Then you send a radar pulse to the Earth, and you measure what you receive back. And optical has the benefit, so in terms of you can think of a spectral response for different materials on Earth. So, for instance, here is some examples where you can see that soil and grass and water, they all look different at different wavelengths. So this signature here is something that we utilize when we try to distinguish different material from each other. Of course, it depends on how good you do that. It depends on how many optical bands you are able to measure. And a standard camera typically have three different bands, R, G, and B, which gives you some limitations of what you can see. Satellite data, or that we will be discussing here, are multispectral, meaning that we can have up to 20 bands, for instance. That in different wavelengths, not only the visible one, but also outside of the visible range. So infrared and near infrared, also something we will have here. Of course, if you have even more wavelengths, in hundreds of wavelengths available, then you are talking about hyperspectral data. But this is not something we will be using in this case. So if you have an image of the Earth, if it looks like something like this is an RGB image acquired in 10-meter resolution. This is from the Sentinel-2 satellites, and it has a repeat cycle of 5 days, meaning that it takes the same image every 5 days. Of course, you can use false colors by combining bands that are not visible. This is where we also include a near infrared. You can see different characteristics. Vegetation tend to be red when the way I have set up this design here by putting the NER first. Other satellites that we will use is Sentinel-3. This is from the OLCI sensor, which is a sensor that is in 300-meter resolution, has 21 spectral bands. Of course, and then you can talk, you can obviously wonder why do you want to measure in 300-meter resolutions instead of 10 that the Sentinel-2 provides you. Well, the Sentinel-3 provides you daily coverage, so you can see the same scene every day, which is really beneficial if you want to do some kind of time series monitoring. And in particular, since the Earth is often covered with clouds, so it prevents you from seeing the scene. Here's another false color image which enhances other features on it. On Sentinel-3, there is also another satellite called a sensor called SLSTR, which is even coarser resolution. It has 500 meters, so you can see the thing smears out even more. But this also provides you daily coverage and even larger coverage than the previous one. And that also has a thermal sensor, which is able to, you can see the temperature on the surface. It has 3 different thermal bands that we can use. And finally, the radar satellites looks completely different. It looks like an image here, but now you're seeing the physical characteristics of the scene here. And white is typically built-up areas, cities. And the black is the ocean, which means that the radar signal is not coming back as much because it's just like a mirror and it bounces away and you don't see it. All right, so this is the data we are using. We will be considering 4 different sensors, the ones I presented here. And now we move into these foundation models. And the characteristics of the foundation model is that they are a model, quite big model, trained at scale using a vast amount of unlabeled data. They are designed to replace task-specific models and serve as the foundation of many different downstream applications. And in AI, this has been a huge paradigm shift, I need to say. And the most popular foundation models we have today is, of course, ChatGPT, which supports originally language. And now, of course, it can also use images and other modalities in it. So this is highly can easily do a lot of different stuff with this model, like summarizing text. You can ask it to write stuff. You can do so much things. So it's quite unlimited potential of the task this model can perform. So why are these important? Well, first of all, it learns from a vast amount of data without requiring the labels. And labels has been a bottleneck in deep learning that's for the to prevent developing powerful models because it's so costly and time consuming to make up all these labels that you need for large data sets. So these models here and reduces the cost and time effort of building new downstream applications, mainly because you require less labeled data in order to make them work quite good. So that means also that they often have a better performance on downstream tasks than models built from scratch. It's not always the case, but it is potential to have that since you can use so much unlabeled data in the training of the foundation models. And another cool thing about these models, they are the potential for multimodal application is vast and it's easy to do in some sense. And this is something we will of course focus on here as well. So summarizing, we skip these task-specific models and try to fuse data into big foundation models and then adapt that to different applications. In this project we have at ESA, the objective is to develop a foundation model for Sentinel satellite data. And then a multimodal Sentinel satellite data. So we don't want to use only one. We will consider 4 different sensors on 3 different satellites. And then the next task is to demonstrate it to use cases related to climate science and society applications and services. This talk will mainly be on the work of developing the foundation models and how that has how that is now and the status of it. So a little bit on the use cases, but not much. So in order to make the foundation model here, we needed a data set, and we needed a highly diverse training data set to boost the performance. So we make sure that it has not only seen vegetation or land cover from a small area, let's say Europe, but we cover the whole variety that we have. So we have used the Sentinel-2 sampling grid as a spatial sampling unit. So this is a grid that each of the Sentinel-2 images is photographed in, so to speak. And we have used a stratified sampling approach to ensure the diversity of the land covers and included in the training data here. So to do that, we have used the ESA land cover, world cover, which is like a land cover map of the world in 11 different classes. You can see that on the top right here. And we have used an RGB composite of the world and other data like where there is ship traffic going on, where do we have oil installations, where do we have sea ice, where do we have icebergs. So those are also areas we have included in it. So from these the world cover, we select classes we have in a tile, and then we try to cluster them, so we have a distinguished, so we can reveal different kind of typical or not typical prototypes of how land cover manifests on the world and try to select it based on that. The RGB, we send a tile into or a small crop into a VIT and use that as a feature, which we then cluster in order to figure out, okay, where should we sample them? And then from these clusters, we sample data. So this is what we ended up with in the end. We selected more than 6,000 different Sentinel-2 tiles. One Sentinel-2 tiles is 10,000 by 10,000 pixels in 10 meters. So it's 100 kilometers. And we have selected more than 18,000 tiles. Because some of them we sampled multiple time instances. That gives you about 20 terabyte of data in 16-bit resolution. So in total, so for each of the Sentinel-2 tile, and time instant, we also selected the corresponding Sentinel-1 and Sentinel-3 data that covered the exact same area. So the data set in the end here is, we can see here from a given area is Sentinel-1 SAR. They have two different bands, two different polarizations. And polarization is just the way the orientation of the electrical field of the radar pulse. And we sampled that in different resolutions using so-called multi-looking, meaning we aggregating pixels, so because that's a common thing to do in radar. So we have that included. Sentinel-2, there's 3 different resolutions for those bands. The 10 meter is 4 bands of that. It's 6 bands in 20 meters, and it's 2 bands in 60 meters. So 7 bands in 20 meter. And at Sentinel-1, there is 21 bands in 300 meters, and the Sentinel-3 SLSTR is 9 bands in 500 meters. So these are our data. So quite a lot of data we need to handle here. The core of the foundation model here we have chosen to use is a vision transformer, a plain vision transformer more or less. I will not go through that. We will consider 2 different versions. So we have a base, which I will talk about in this case and show results from. 12 different transformer layers, and the large has 24 different layers. And each of them, of course, has a multi-head attention, and I think it's 12 layers of that, and so on. So this is the standard one we use here. So in order to make it work here, we handle the multiple sensors at the native resolution. So we don't rescale the 1,000 meter data to 10 meter, we just use it as it is. And we support, so there have different patch projection layers for different sensor bands. So each band has its own patch projection layer of weights that we will use to convert it from a patch size, as a patch could be 16 by 16 typically, or something else, to this vector, embedding vector of dimension 768. And then we are pooling these patches for each sensor. So the 10 meter bands will be pooled to 1 by simple averaging. So these 768 vectors, the 20 meter band, we do the same, and so on for all these. But I think except for the Sentinel-3, we have, I think we divided into 3 different groups because there's 21 bands there. And then we have doing the masking of the patches. So we are using a masked autoencoder principles. That's the main to train the model. We mask them, and the ratio is about 75 to 80%. So what's more on this? All sensor input images cover the same ground cover. So meaning that if you have, let's say, 1 kilometer by 1 kilometer is Sentinel-2 image, meaning let's say 100 by 100 pixel, we have the same one. That will be just one Sentinel-3 pixel that will be included here. And this ground cover is randomly sampled from a set of candidates. So we will randomly sample how big this should be, from 1,000 to 32,000 meter. We are also thinking about extending it a little bit more to more than 32,000. But also the patch size is randomly selected from a size of 6 to 32 in this case where we are now. So we don't have to restrict ourselves to a specific patch size, which is a little bit different from many of the other foundation models that has been developed in Earth observation, which are locked to say 16 by 16 pixels. Yes, so these are after masking sent into the VIT, the encoder, and we have a bunch of tokens. And of course that moves into the attention matrix. So we are computing the attention between all tokens that we have from all the groups, all patches. So it could look like this. I've skipped a lot of sensors here, but this is how we typically do. And we compute the attention matrix and learn that. Of course, it will be different patches that moves in because from each time you do it because of the randomness of the mask token approach. And in order, since we are using a flexible patch size, and that is randomized during training, we need to move into this so-called flexi-VIT approach that was developed a year ago. So we have done that here, and the patch side, we need to encode that as a encoding to them, so the VIT knows what the patch size is. And more importantly, we need to change the weights of the patch projection layer, since that will be different from each time. And here we just interpolate that, and that is the approach they did in the flexi-VIT approach. Interpolate the weights so that when we just reproject the patch, we have different weights for each patch size, so to speak. This is done by simple interpolation. Of course, different from the VIT is that the flexi-VIT is that we are working with masked image modeling or masked autoencoder. So we needed to modify the loss, and we figured out that by using the pseudo-inverse of the interpolated weights, we were able to easily compute a loss by just considering that. Of course, in the end, there is a budget of the number of tokens that we can use, since we cannot just put an infinite amount into the VIT. So if we typically have a very small patch size, we cannot have a huge input size of the image. So that is what we're constraining the budget with. But in principle, we can also use different patch sizes per group. There's nothing from stopping us to do that. And then challenge with all these different sensors, different groups, the flexi VIT approach. We needed, and a normal transformer has a positional encoding incorporated. Typically, it's a sinusoidal type of encoding to encode which patch is it in the grid. And that was very that didn't fall out that easily for this case here, since we're changing the patch size on the fly. So we instead using something called Alibi that has been applied in NLP for a while, but there's also 2D versions of that. It's also been applied in a foundation model for Earth observation called Chroma. So we have used that as well, which simply just scales the attention matrix by computing the distance between the tokens in the grid. So here is just an example how this 20-meter patches relates to the 10 meters patch, the distance there, and so on, and vice versa. So this is what we included. And of course, for the whole thing, it looks like a quite complex matrix that will be the alibi matrix or attention matrix in the end. So this is how the encoder is designed. During training, the main principle is this masked image modeling or masked autoencoder. So at pixel levels, we reconstruct all sensor bands. So because we have masked out 75% of them, so we reconstruct them here. And that is one task. The other task, in addition, we do classification of a scene classification map that is attached to the Sentinel-2 product. Mostly that includes clouds and cloud shadows. That is very important for us to mask out or know what is. And then we have a world cover. So we try to predict the classes included in this world cover in 10 meter. We predict something called ESA globe cover that was developed a few years ago, and that is in 300-meter resolution. And also the American satellite MODIS, or the sensor MODIS, also has products for land cover, which we also use, something called Mod 12Q1. So all these are predicted in training, in addition to the sensor bands. In addition to this pixel level mapping, we also perform a prediction of Era 5 land cover, and the latitude where the image is taken from, longitude, and which month are we now. We'll come back a little bit to that later. So this is on the image level. This is done by just averaging all the tokens for the crop we are looking at, and using that as feeding that through a projection, a linear projection, in order to predict what we have here. In addition to this masked autoencoder loss, we have also included a contrastive loss. Because these reconstruction approaches scale very well, but the learned representation that can require significant fine-tuning in order to be useful. So this is a little bit of weakness of that. So we have therefore also included a contrastive loss to improve this representation here. And what we have been doing here is something, this is on still going work, but this version I'm presenting here is just saying that two patches from the same crop is positive or the same, and two from different are negative, and this is the contrastive measure that we used in the computation of the contrastive loss. We have extended this by now also including the land cover in order to make sure that the patches that are similar are really similar, and two patches that are supposed to be different are really different. So we will see how that works out later. In addition, yeah, for the ERA 5 is like a climate data set that consists of a lot of variables, and we have used that here as well. Here is some example. We have changed this a little bit, but in the end, you can see what we are talking about here. It could be wind, it could be temperature that is 2 meters above the ground, potential evaporation, snow, surface pressure, these kind of things. Not all of these are directly measurable by remote sensing data, like surface pressure. So what you will see there is typically elevation. Things that tend out to go high up on mountains in high land have lower pressure. It doesn't have to be like that, but this could be one thing, and all these things. In addition, we have also included something called FFT loss that we just saw on our presentation, could make the training more stable. And then, yeah, this is about it. Where we have now, the total loss is consisting of the master autoencoder or master image modeling loss, the contrastive loss, the ERA 5 loss, and the FFT loss. So just an example of reconstruction here, doing quite well on this one here, of course. The reconstruction is always a smoothed version of the image itself, and this is what we have seen all over the place. Here's another example on Sentinel-1. You can see this also reconstructs, but still a little bit more smoothed than the original image. To benchmark the model here, we have been using something called a Pangea framework that is developed in the field lab community, meaning that we take the model we have, we freeze it, we don't change the weight, and evaluate that on a specific set of data sets. So there's a lot of them. And by doing that, first you can also select how much training data you want to use. And when we did that on this 100% training data, we did okay. It's not the best one, and here you can see that the unit is actually doing good on these benchmarks. It's really hard to beat the unit, and that is the really benchmark. There is some model that's called Teramine who has been doing this, so they are probably better than unit at this case. But when we move on to just using 10% of the training data, our model is really making a good progress here, and really shows that we outperform all the others quite a lot, actually. And we are super happy of that, because this is where we want to move with a model having as little training data as possible, and to perform well then. So, but this is, I must say, still ongoing work. So we are continuously evaluating it, and particularly figuring out the impact of different patch sizes and all these things. So that will come later. This is just by a pre-selected patch size of, I don't remember, 8 or something like that, and tested it. So there's a lot of more evaluation to do, and it's only evaluated on Sentinel-1 and 2 data, so on 10 meter. So this is also something we need to do, is to evaluate on data with coarser resolution, like the 300 meter potential. So there are other benchmarks that we will include there. So in order to adapt for our case, it is also in this project we need to do that. And what we typically do there is like we freeze the encoder, but in many cases there's also a need to add auxiliary data, meaning that it could be very useful data that could support the satellite data. For instance, a terrain model slope or any derivatives of that. Could be passive microwave rate data that could be interesting to have, because that's really, really powerful in distinguishing thing, but has some other drawbacks. So it's just auxiliary data. So this is something we are working on, how to do that. There are lots of different ways. I will not talk much about it, but you could, for instance, have a tiny VIT where you send it through and then just merge the tokens after the encoder and use that as a way of doing it. So there are an infinite amount of ways of doing it. I will just show some examples here for two cases, snow mapping and sea ice. Snow is a very important for the climate here on Earth. It affects the weather patterns and all these things. And there are today a lot of projects also funded by ESA that works on just having a good estimate of the snow coverage. Here we can see how it goes through winter to the left, through the summer months. So how it affects it. So we have a lot of data in-house at NR and use that to train this downstream application. So that is based on just using high resolution data, not high resolution, this is Sentinel-2 data and quality ensuring that in order to make it robust. So this is what we have used, and then this pipeline will be take this Sentinel-1 and Sentinel-3 data. Sentinel-3 is the most important here. Send it to our model and adapt it to different cases. So we will consider snow cover fraction, snow wetness, and snow grain size, which can all be estimated from remote sensing data. So here's an example of snow cover fraction, which is definitely the most important one. Where we have sent, this is Scandinavia back in 2018, I think, something like that, the image. Totally snow covered all over except the southern part of Sweden. And the purple color is 100% snow cover. And we were happy with this because we were able to actually predict the high snow coverage in the forested area, which can be challenging. We also have some very, very low snow cover predicted in the southern part of Sweden, which is of course wrong. But yeah, so this is something we will work on. It's not high, it could be like 5%, so it's not something critical. So it could be probably masked out or something like that, or work on this in order to make sure that we are getting our representative data to adapt this model. But the mean average error is just 2.7, so which is quite good. We also explored it on sea ice, estimating sea ice concentration. This is really, really preliminary results, still ongoing. So this is just the early version is back from April, I think, when we did this. So here we also have auxiliary data, and that is passive microwave from the AMSR2 satellite. Challenge is a severe class imbalance. So they have 10 different classes or 11 different classes from open water to 100% sea ice concentrations. So in steps by 10%. And vast majority of the data is from open water and full and 100% sea ice concentration. So the same principles apply here. We take Sentinel-1 data in this case, send it through the model, adapt it, and now we also include the passive microwave data and try to estimate the sea ice concentration. So here are some preliminary results. We skipped all 10 classes for now and just used 3 of them. So we said we have open water, we have some intermediate sea ice concentration and 100%. And this is something we were quite happy with. We were able to actually capture the general trend of this and to see how it works out. And yeah, so far so good help. The over accuracy on the 3 classes were 83%. And here is also, I expect the annotation is more on a broader scale. So it's like taking an area and saying, okay, within this area, the average concentration is 30% or something like that. So, but in that area, there could be patches of 100%, there could be open water and so on. So it's not super precise in terms of going per pixel. Yeah, here's another example. You see the same trend. It has a lower concentration and then a higher concentration. So we can see the gradient going from open water to 100% sea ice, which is quite good. Of course, the ground truth, you have a lot of more classes, so it looks more complicated. We have also 10 plans to do, or we need to do, for other applications as well. These were just snow and sea ice I mentioned. We will just started to look at iceberg detections. We need to detect icebergs, so we need to develop a detection module that works on this. And drought monitoring is something we will do as well to measure the risk of the vegetation being affected by droughts. Flood, something we have been doing now, it is starting to evolve, and wetland is also something we have been doing for a while, and oil spill is a new application. The oil spill is part of this visual intelligence project, the center, in collaboration with the Kongsberg Satellite Services. All right, I think I'm about to sum up. So what we have is one model for analyzing satellite data provided by 4 different sensors for land and ocean environments. And this support models, this model here supports resolutions and sensors from just both SAR, multispectral data, and a vast difference in resolutions from 10 meter to 1,000 meter. So same data can be used in the same model. And it don't have to be single sensor. We can apply it to a combination of them. We can have missing modalities in between. It doesn't matter. This works. The core of this is a VIT, but we wanted to be highly flexible and to support different input ground covers and patch sizes. So this is something we think is important. It also, in terms of you go very fine grain segmentation, having a smaller patch size could be beneficial. But of course, the drawback is the compute. So it takes more. We have more tokens then, and it's more compute in order to do it. We plan to launch 2 different versions of it, a base and a large version. And they will be freely open for download and available soon. We are writing on our archive paper right now and we will also aim for publishing that after we are done with it. Yeah, of course, the next challenge for us here is this downstream application to really show the benefit at those as well. Yes. So, and also data will be made available if Hugging Face wants 20 terabytes of data. So we are okay with it at least. Good. That's what I have. Thank you.